Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So Aristus hardly needs an introduction. I think most of you have seen him. He's been here almost 2 years visiting from Technion. And he'll give us a talk about concurrent garbage collection and some of the work he's been doing here and maybe before. Or is it all from here, from the last 2 years? Okay, great.
Okay, thank you for the introduction. And well, it's good to see so many people from various places. Okay. So I'm going to talk about the real-time garbage collection. That is the projects that I've been doing mostly here during my sabbatical. And this is joined with Bjarne, whom a lot of you know. He has an amazing, deep knowledge of the system, and he has excellent ideas. It was really great to work with him. And Philip Pislow was an intern that came from Purdue. He was doing garbage collection and real-time before he came here, so he quickly got into the business and he implemented a lot. He had, excellent ideas, so it was great to have him. Gabi came without any knowledge of garbage collection or compilers or anything, but he was very smart, so that's why we brought him. And he also got into the business very fast and helped us in a very delicate point in this project. So this is all of them, as you can see. This is Philip and this is Gabi. That guy sits in the back. And this is, you see a moment of hard concentration on the challenges. Okay. So I'm going to talk about real-time and real-time. And not going to this crowd, I'm not going to preach for hours why real-time is good and why garbage collection is good. I assume this is known. But real-time is about responding on time to events. And there are lots of systems that require that. Recently, if you're riding an airplane and you want to make it go up, you don't want to wait for a while until it responds. It has to respond on time. Stock commerce is maybe surprising to some people, but they really need to respond quickly to a share getting to the right price. And I've heard that a broker saying that if they have a 9 millisecond pause time, they may lose the entire day profit. So they really have to respond really quickly. And there are various systems that require real time, and predictable response is what people really need. They don't care a lot about efficiency. So the system could go a bit slower, but when an event comes, we have to respond to it immediately. You don't want to be too low on efficiency because eventually you will not respond to the events, but reasonable overhead can be accepted. And today, if you look at commercial real-time collectors, they respond within 1 millisecond, maybe half a millisecond, and we wanted to go a lot below. So we targeted it 100 times better, and well, we did it, so that's why I'm here, and I'm going to talk about this project. So managed code also, I'm not going to preach for it, but historically, real-time was done in assembler with some verification. Really small tasks were running in real-time, and you couldn't do anything meaningful. And recently, with all these more interesting applications, people have been starting to wonder if they could run their project in Java or in C# and still get real-time. And then garbage collection is one of the major obstacles. Of course, you cannot have JIT, you cannot have class loading during the run, you cannot have all these things that make pauses. But garbage collection is even if you're an ahead of time compilation for Java, still you have this garbage collector that creates pauses that is not good for real-time. So Sun's immediate response was a real-time specification for Java, which basically said that if you want real-time, just don't use the heap. There were some threads that were responding on time to events, and they were not garbage collected. So we need a reliable...
They could still allocate memory, but they had to manage the memory allocation themselves?
Yeah, there are various flavors of how people did that. Sometimes they didn't allocate at all. Sometimes they didn't use garbage collection, but a release. But you lose all the advantages of a garbage collection for Java and C# if you go that way. So we really wanted to make the garbage collection not interfere the fast response. Okay, so what do you need? When you have a parallel platform, you need four things. And so first you want to have no GC pauses or almost no GC pauses in order to be able to respond on time. This is clear. Now, you also want not the garbage collection to not start grabbing locks. So when the garbage collector does something, sometimes it's very convenient to say, I take a lock, now the program cannot do some things, and then I do the delicate things that I need to do, and then I release it and the program can continue to run. For real-time, this is out of the question. If you talk to the real-time community, they have this example of this shuttle on Mars that kept on shutting down and restarting because a lock was inappropriately taken by. So you need no locking and lock freedom support from the garbage collector. A third thing is you want to avoid worst case fragmentation. And this is some consensus that has developed in the memory management community that real-time, since it is a worst case scenario, you really don't want to avoid moving objects as mark sweep collectors do. We don't have any benchmark that really shows that this is necessary. I have seen some benchmarks, really long-living benchmarks in IBM when I was consulting that had a problem of fragmentation. Normally when you run benchmarks that usually people check their programs, you will not see this, so it will be very difficult to judge this. But there is a consensus that if you want real-time, you must be able to solve fragmentation. So the problem is, if someone doesn't know what fragmentation is you allocate and you release objects. If you don't move them, eventually they may cover random spots in the heap, and now comes a big object and you cannot allocate it, even though you have enough space, but it's in holes that are not consequent, so you cannot allocate this larger object, and then you're stuck. So you need to be able to move some objects to clear some space for allocation. Okay, so, and of course you want as low as possible overhead and scalability. So this project is the first to provide all four of these. Now, if you want to give up, if you're giving up any of these, then you can find in state-of-the-art ways to do that. So if you're giving up lock freedom, there is a moving collector that does pretty well. If you're giving up partial compaction, online concurrent mark sweep can do the work pretty well. If you, with some modifications, well, you must care about short pauses. If you give up the overhead, so you're really willing to have a large overhead, then there is an existential work that shows the possibility of doing lock freedom for moving garbage collectors, but then you have a huge overhead. You basically allocate for each pointer modification. So to do all of this, it was not possible before this project, and this is our contribution. Okay, so what did we do? First, we introduced these real-time concurrent compacting and lock-free collector, and we have three different alternatives. You'll see what's the differences and trade-offs between them. I'll talk about them mostly in this talk. We also introduced path specialization, which is a compiler optimization that helps to reduce the overhead a lot for this project, and also may be used for other garbage collectors that we hope it will be used. We had a project on lock-free incremental stack scanning. If you do everything right, stack scanning is going to be the bottleneck. And that we did we did a work on that, and I will not have time to talk at all about this, but this is a delicate lock-free algorithm that we introduced, and then we wanted to understand what lock freedom means for garbage collector. And we looked at previous work, and people had different notions. What does it mean? The garbage collection doesn't take lock. The program is not forced to take locks. There were various flavors, and we wanted to formalize that. And when we got to that, we first wanted to check what lock freedom is. And we went to the community of parallel and distributed community, and we saw that there was basically no definition there of what lock freedom means. So it was surprising to us because this notion has been living for a lot of years, and each of these papers had some short definition in the abstract, and that's it. So we formulated lock freedom, and we formulated what does it mean for a garbage collector to be supporting lock freedom for the program, and that's a kind of a theoretical work that emerged from this project. So in terms of publication, the first version of the collector was published in ISMM 07. The other two, plus a comparison, will appear in PLDI in 2 weeks, and this compiler optimization will appear in ISMM in 2 weeks, and we're still preparing the incremental stack scanning. We're in the end of that, and this formalization we have submitted to the parallel and distributed community, and we're really interested in their feedback, what they will say about it. Okay, so and in terms of Microsoft, we have filed 6 patents. 4 of them have already been filed, and 2 of them are being, we should respond to the attorneys. So this is all Microsoft technology. We have some indication of, we have one large external client who is really interested in short pauses and is thinking about adapting Bartok. Just for this purpose, this is all incorporated in the Bartok compiler, which is currently in an incubation. It's not a product of Microsoft, but this is another selling point for Bartok that may help it succeed. Okay, so what do we, so I'm going to, so from all of this, I'm going to really try in this crowd to dive into the technical challenges and explain how we solve them, more than just give you an overview and buzzwords on what real-time and garbage collection means. And if you want to improve responsiveness, what do? The first thing that comes to mind is just to have concurrent garbage collector. So you want the garbage collector to run on a separate thread, and then the program doesn't have to deal with it and can respond very fast to any event that comes. This sounds very logical, and this gets you the high responsiveness, but the problem is that we don't know how to do it. We didn't know how to do it, and what didn't we know? The main problem is that we have to move objects while the program is working on them. So if we want the compaction, we need to move objects. We cannot stop the program for that because it's a real-time system, and objects are going to be moved, and the program has to be able to deal with it and go on working. And this is the main challenge that was, yeah.
Long time ago, Dijkstra had an algorithm for this, right?
Mark and sweep, you mean?
No, a concurrent garbage collection.
Yes, so he had, yeah, there are lots of mark and sweep concurrent collectors. They don't move objects. And in the real-time systems, you don't, I mean, there is a consensus that you really have to avoid fragmentation. If you decide that your system is okay with not moving objects, there are easier solutions. Yeah.
So yours is the only algorithm that does concurrent GC with moving objects?
In a lock-free manner, yes, appropriate for real-time. Yeah. So as I said, if you give up, if you're allowed to take locks, there are other solutions. There are various solutions if you, give yourself a reduction from what a real-time system needs. Okay. So what's the problem about moving objects concurrently? So at a certain point, there has to be a case where there are 2 objects, one of them in the system, in the heap. One of them is the original version. The other is the new version. Data is going in this direction, and the threads have to know where to access a field that they want to change or read. So if you look at this, if a program comes and there are 2 objects, and he has to read that purple field or write it, and so he has to check some status words telling him until where this has been copied. So if it has been copied until here, he should access this field. And so he reads this status word, and then he goes to change it. But as he's going to change it, actually the concurrent collector moves and copies more fields, and then his write is going to appear here, but other threads are already reading this, and his write is going to be lost. So that's not good. So this is a serious challenge. What you really want is to atomically access some status word and this field. If you could do an atomic access to these 2 fields together, then you could solve it. But the current hardware does not give you that. There are, intentions to allow that in future systems. It's the reason they don't do it is because it's expensive to implement, but maybe it will be possible in the future. Currently, we cannot do that.
But you can implement a decast from a cast, right? There are papers to do that?
Basically, we are doing something similar. I'll talk more about it. So, generally, if a lecturer, if you ask a question that the lecturer knows how to answer, you'll say it's an excellent question. If he has a slide, he'll say it's an amazing question. And if he doesn't know, what to say, he'll say, it will be better later in this lecture. I will come to it. And so your question, no, but seriously, this one really has. I'll talk a bit about it. Actually, I think at the question time, I'll talk about it. Okay, yeah.
Sapphire system, Boston Hudson and possibly other people tries to do something like this.
Right. If you allow yourself to take lock, so the Sapphire system is very related in the sense that if you allow yourself to take a lock, then they can do it. The real-time people are unhappy about it. So if you want to move these objects and you're saying, let's put a lock. No one touches it while I move it, and now I move it, and then I remove the lock. People can touch it now. Then it makes this very simple. That's what the Sapphire system does. They have various implementation. Do you lock the entire object? Do you lock field by field? You're trying to do, but in the worst case scenario, what's going to happen is that the garbage collector is going to lock somewhere, which is needed by the program, and then will sometime lose the CPU. And that's what happened on the Mars shuttle. It kept up resetting because it just lost the CPU with the lock. And then everything went bad. Okay, so we need to atomically access these two locations, the status and the field, and we cannot do it with with hardware that we have today. So we have to solve it somehow. We're going to present three alternatives to solve it, which we call stopless, clover, and chicken. Stopless will have an intermediate long object. I'm going to talk about it soon, so I will not give an introduction. Clover, it locks with extremely small probability. And when I say extremely small probability, it's going to be rigorously defined. So I'm not going to say, maybe, I'm going to wave hand and say, maybe the cache will not miss twice, and then it's really low probability. I will give you a real distribution space. It will be clear that this is a low probability. Okay? So this will be clover. Chicken is going to adopt the strategy of just giving up if there are problems. So it will chicken out. If there is any problem occurring in the system, any concurrency problem, it will chicken out. And all of these require a lot of overall engineering and work that I'm going to ignore. And they are available from state-of-the-art garbage collectors. So if you know the state-of-the-art garbage collector, you can do all the things that are needed to put these things into a system that gives you a real-time solution. Okay, I'm just going to concentrate on the new things, on the novel things in this work, and not cover a lot of engineering works that I cannot fit in the time that we have here. Okay, but the overall pictures, you take a concurrent mark sweep, and you have to change it a bit. Most of the concurrent mark sweep collectors are okay for this. You change it a bit to make it lock-free. So there is a bit of a change. And then you concentrate on doing the partial compaction concurrently. So you move objects only when the heap gets fragmented. And since for our benchmarks, the heap never gets fragmented, we do it every 5 collections. And people do it. This is the standard way that people measure the systems. Today, with the benchmarks, they don't need these moves. You take fragmented pages and evict them. I have, so suppose these are the pages. So you can have some rule of thumbs. There are various ways you can decide which page is fragmented. I think this one looks to me fragmented. So what I'm going to do, I'm going to move the objects out of it, and then I'm going to have this space available for future allocations. So we evict fragmented pages, and then we can use any of these 3 solutions to move the objects out of this page. And then you need to fix the pointers. These objects that moved have pointers from outside and you have to fix it. So you either do it in the next mark sweep collection, because then you traverse all the live objects, or you do a special pass to do it. Yeah?
So, the assumption, it seems like, is that you're dealing with objects of different sizes. Does it
Sure.
simplify the problem if you segregate the objects into size classes?
It simplifies. So if you're in a Lisp system with all objects in the same size, it doesn't help you to move the objects concurrently, but it helps you allocate. So here, you have to find a place for them. That's orthogonal to the problems of this work, but it helps you defragment. So it helps you, get things compacted and the rest free. Okay. Okay, and these two things can run concurrently. So while you're mark sweeping, you can move the objects. They all work concurrently with no problems. You can use two cores, one of them to do the mark sweep, the other to do the concurrent compactions. The rest can run the program and forget that there is garbage collection. This is a bit cheating because it will not forget it. There will be an overhead, and this overhead will be via write and read barriers. So write and read barriers are pieces of code. A write barrier is executed whenever you change a pointer. You're doing something to help the collector. And a read pointer is something that is executed whenever you have to access a pointer. And then you need, basically, the read barriers. So the typical purpose for a write barrier is to tell the collector that something has changed. So the collector is usually going through the graph of objects, traversing it and trying to decide which is reachable. And if you change a pointer, you have to tell the collector, I've modified a live object. And then the collector knows how to not miss some of the objects, although the graph changes while it is scanning. This is a standard problem in concurrent collectors, and I'll not concentrate on it. But there is this write barrier that you have to know this term, because I'm going to use it a lot. It's executed whenever you change a pointer, and the read barrier, usually you execute some code to find, if you have two copies of the object, you have to find which of them you're going to use. So the read barrier is executed before you actually read and tells you where to go. Okay, so let's start with stopless. That was the first one. And the basic, just to remind you, we need atomic simultaneous access to the status and the field. Status of the copying and the field. So what we're going to do, we're going to create a temporary wide object in which we'll have this, each field will have a status just next to it. And modern hardware does allow you to do a compare and swap, or to atomically access a double word. So we're going to use that. And we're going to, so in general, we're going to move the original object into this wide object in which we'll have this, each field will have a status, which we don't have normally when we run. And then from this, we're going to move to the target object. Okay, temporarily for each object that we need to copy. Okay, so we need two protocols. One protocol moves from here to here, and then the status field is in the target object. And when we move from here to here, the status field is in the source object. So we need two protocols to let us deal with both cases. So the first one, yeah.
So the status field is something that is only needed for the collector.
Yes.
And the field is the actual object.
Yes, right. The field comes from, so this is the original object. It has some header and lots of fields, words.
What the status is indicating?
So the status will tell us where the actual data is, where you should access it. So it can say, you will see it more and more, but the status can say in the original, in the wide objects, or in the target object, and then you know where to go to look for it.
So it's actually just a few bits.
Yeah, I mean, if you had a bit for each word that was dedicated for the garbage collector in the hardware, it would be excellent. We could use it. But 33 bits is not what Intel would give us. So maybe next year. Okay, so what do you do in the first phase? In the first phase, you need to move this U. So whoever comes to access this field has to copy it. This is for this part of the solution, the program threads are going to help the collectors. Whenever they touch a field, they will only touch it in the wide object in this phase. And when they touch it, if it's not there, they're going to copy it. So everyone, the collector is going to do it systematically for all fields. And each program thread that wants to access something will copy it and access it here. How is it done? You read the status. You see that it's still in old. Of course, if it's in wide, then you can just use it. You don't have to do anything. It's in old, and then you read the old value, and you try to simultaneously change the status and write this word into it. So you say in wide and you. Okay? If you failed and someone else did it, then you can just go on working on that. You fail a compare and swap when someone else does a concurrent compare and swap and puts here his value, but his value is going to be the same. Everybody is trying to install here the same value. So if someone wins, he's going to, you don't care. You just go on working. So it's important that you don't care because you don't want to wait forever. You want to have a bounded number of instructions that you do and then access the object. Okay, so you atomically write and then you access. You don't care if you succeeded or not. You just access this field. Yeah?
How did I know that actually that there's a wide object?
So you have this. Okay, so in the header, there are various indications of what's happening. One of them says this object is going to move. You decide it beforehand. You're going to evacuate pages. There is some thumb rules that you use to decide. And this object has been decided. It's going to move. Then during the copying phase, there will be this pointer that points to the wide object. And you can use all this information to...
So in my program threads, every time I want to go through a field, I have to check the header first now. So I'm paying an overheads for every access.
Right.
Regardless of whether I'm copying or not.
Right.
Correct? Okay.
Yeah. This is so.
This is the
No. So okay. So if you're not copying, you can. So there will be phases. It's an amazing question. So, so we're going to talk about it. There are phases. So in the copying phase, this is what's going to happen. In the idle phase, it's not going to happen.
Yeah.
And now you can ask.
You have like different versions of the program you can switch between?
Okay, this is another amazing question. But this is. So we're going to talk about all this. Good. Okay. So, but there is a read barrier, and you have to decide where you're going. Yeah, and it's an overhead, definitely. So, yeah.
So, are you assuming that the fields that the program can define are not going to rely on double word atomicity themselves?
Another excellent question. So this relates to Shah's question. If you have a wide, so we are going to. So sometimes the guy uses a double word compare and swap. Otherwise, we can deal with it. But if it uses a double word compare and swap, then we have to resort to something with a larger overhead. And this is not our invention. There is, and this is, I think, what Chaz was referring to. There is a work by Tim Harris from Cambridge and two more guys that are not from Microsoft. And and they do it. They have a general algorithm with a much larger overhead, which will do this. And if someone does a double compare and swap, we have to resort to that thing, which I'm not going to discuss in this short talk. Yeah, but this has to be dealt with.
And that applies only during the copying phase?
Yes. Okay. So the collector does this systematically to all fields. The program does this before accessing a field. It's a read barrier thing that happens during the copying. You can see that this is, there's no loop here. This ends after a few instructions. So you have responsiveness. Okay, so now let's go to the second stage where I have the status in the source and I have to do the same thing. So what happens here, only the collector does the copying. The program does, we'll talk how the program handles the reads, but the collector, what it does, this is in the wide, he wants to move it here. So he's going to copy the value from the wide object to the new object, and then it's going to atomically write, this is in new and this is, and then the program will know that it has to start walking on the target object. for this field. Okay? So this is the second. This is done only by the collector. It would have been nice to let also the program threads help, but we just don't know how to do it. Whatever we tried failed. So it doesn't mean that it's not possible. It's possible if you have a huge overhead, but if you're not allowed to take any locks or nothing, we just don't know how to do it with program help. So only the collector does it, and I have no time to explain the difficulties, but it just it's a problem. In any case, only the collector copies the field. When the program needs to write, if the status is in new, then you know you can work on the new object. There is no problem. Otherwise, you write to the wide object and then you check again. If after you've written, this has moved to the new object, then you go there and write. This is also, bounded thing. This is what the program does. It's very important. There will be a bounded number of instructions that run, and then the access to the memory occurs. Okay, so we are within limited responsiveness. Okay, so we have these two protocols, and yeah.
Does that in any way change the memory model that the program is seeing? I mean, are you adding any visible writes there, or is this completely transparent?
So what we have lots of classes all around. So initially, when we planned this, we did not think about we almost did not think about the memory model. We just designed an algorithm, and I think that's how people usually do. And then we went over that, and we thought, what would happen if? And basically, most of it was okay already, because we have so many classes here. We assume a class, a compare and swap, gives you a memory barrier, a memory fence, for which nothing can go above or below it. And that was basically, because we have so many classes, it was basically enough to do the work for us. We haven't thought a lot about what happens if the original programs rely on some very weak model, and now we're making it stronger and maybe changes, efficiency. There may be things to think about it, but we were concerned about correctness, and this we can provide. Okay, so we have these two protocols. And it's important to see there is a bounded number of operations for each program barrier. You never get stuck. You never wait for a lock. You never wait. You just do what you have to do and go on accessing. So we have a lock for, yeah.
That's a great question. So, the phase from going from old to new, there's no new phase going from new to even newer while the program itself may be modified.
You mean, so there are two phases, right? Going to the wide objects and going from the wide object. But there could be another garbage collection later. No, so you finish copying all you needed to copy in order to clear some space for allocation.
That synchronizes with the program.
Yeah, right. So I'll talk about that. There are phases, and there is synchronization for the phases. We'll see how it's done. We need not to block there too. But this is not a new thing that we've done. This is something that is known how to do for collectors, concurrent collectors. Okay, so to summarize, we have an intermediate temporary wide object. The status word is used to help us touch the two things simultaneously. Full lock freedom, bounded barriers, so we have real time, very short pauses. The disadvantages is that you have space and time overhead. Not really bad, but not very good. Yeah.
So what's the worst case space overhead?
So the space overhead is something that's really difficult to measure, because if you let the heap grow, then you can wait with the collection more. You can. There's no fragmentation in real benchmarks. It's really it's a slippery slope to try and claim something really serious. But we just we didn't see any space consumption that was more than 45%. But it's something that's very difficult to say. How many objects are you evacuating? How many wide? So do you allocate all the wide objects beforehand, or you allocate them when you need them? How much time does it take to collect? Because while you're collecting, there is allocation, so the heap grows.
You need to know the maximum possible and out of memory here.
Sure, sure. I mean, usually in real-time collectors, you assume that you're going to have enough space. In general, in a concurrent collector, you start working and there's more allocation, right? And if you allocate like crazy, you're going to be out of memory. That's clear, and any real-time collector will fail if you allocate like crazy and you don't like the collector finish. I think we haven't done a lot of engineering process to try and do some static analysis to check that the program is not allocating like crazy. There is work by, I think, Ron Citron and a student who are trying to make sure that the program doesn't have crazy phases that will destroy its real-time behavior. All the collectors that we know ignore this. You know, when you say hard real-time, you should be worried. There's no really hard real-time. There'll always be a way. You really have to close all the corners in some way to avoid problems. But this is, you're right. If I'm concurrently trying to get the garbage and someone is allocating like crazy, and I cannot allocate, and I cannot reclaim that, then it's going to be out of memory. But usually we take a very large heap and to start with to make sure this doesn't happen, and we try to work in a reasonably efficient manner. Bjarne wants to also answer this?
Yeah, so we did the very stupid implementation. We did not do it a good engineering job, if you will, when we computed the space overhead. If you really want to only evacuate objects from pages that are not very populated, then you could allocate the wide word on those pages themselves. So various tricks you can do to basically have zero overhead. We'll just allocate them somewhere else, and this is the worst case we're basically seeing, right? If you're dumb. You could be a lot smarter with various
Right, they're very smart things. So we should attribute this to Tim Harris, right? Tim Harris, when he first saw the paper, he said, you can use the space. If you have a defragment page, then you have lots of space in it. Then you can. But these are engineering tricks, right? We could use lots of them, but it will not help the mark sweep collector. Yeah.
These overheads are compared to what? The baseline collector, or?
Overall running time compared to a non-copying collector, just concurrent mark sweep. Yeah.
The header word you had in the implementation was able to be overloaded to fit the needs of this algorithm, or was there an extra header word?
We added two extra header words. Okay. One of them for forwarding pointer and one of them for all the other things we needed. Yeah. Forwarding pointers, I think, is standardly used. Yeah, but there is a space overhead for that. Actually, I have measurements which I will not have time to present, but if you want, I can show you exactly how much each header word costs in memory consumption and how much the intermediate object costs, and all of that is measured. Yeah?
So the two phases going from the original object to the wide and then wide to the final, they overlap, right?
No.
So you first do all the wide.
First move to the wide, then, yeah. You could do differently, but that's how we do it. Okay, so Clover is the probabilistic thing that we want. So probabilism is very much accepted in various communities, but not so much in the programming languages community. People don't like that there's a probability that something fails, and I'd like to preach for it a bit now. First, it has to be a well-defined probability space, and in this case, what we're going to do, we're going to choose a random value pi of a double word length, and we assume pi is never written to the heap. Okay, this is the probability space. We choose pi, and it's independent of the program run, and the program doesn't see it. It doesn't work based on it. It doesn't know it, and we just want to look at the probability that the program doesn't write this value to the heap. Okay, so we have, if it's a double word and it's a new computer, then it will be 2 to the minus 128. Probability that a write will actually write this value, and it doesn't matter, what the program does, even if it's adversarial. So it can't be too much adversarial. If there is a malicious code that tries to find pi and write it to the heap, then it's going to fail. But we assume the program wants to be real-time. If it doesn't want to be real-time, you can just take a lock and wait, right? We're not fighting the program. But the pi is going to be independent of what the program does, and so you can think of it as if the pi is chosen after the program finishes. So let the program write whatever it wants, and then I toss coins and see if I hit any of these writes. Because it's independent, I can do that. So this is a really low probability. And then to use it, it's very easy, because now I have this kind of status thing that I can put into each word. If I write a pi in the original object, then it's not the program who wrote it, it's I who wrote it, and now it means that the field should be accessed in the target object. Okay, so this is very easy. If the collector copies everything concurrently while the program is running, reads the value, I think I have this, so he reads the value, copies it, and then he atomically writes pi here, assuming that u has not changed. Okay, the collector does it, the program, maybe it says here, yeah, the program just uses this unless it's pi. If it's pi, it moves to use this, and this is a bounded read barrier, and the program can respond immediately. Okay, so then there's the question, and here I'm preaching, what is really a reasonable probability to be used for failure on even a real-time system? Okay, so what is the probability that I will die tomorrow? In general, in the US, the number of people that die each day in a car crash compared to the number of people overall is 1 over 300,000. Okay, this is in the US. Hardware failure, so I may die tomorrow with this probability. Hardware failure will happen in my computer with larger probability. Is it okay to lock with such probability in a real-time system? And if you look at Clover, it locks with probability 10 to the minus 20. I think it's perfectly fine, to be used in a hard real-time system. Although I know there is some objections to use probabilism. This is really very low probabilities, and I'd be preaching to use this. Yeah, you wanted to object? Or?
I'm curious about the threat model here. It seems
the what?
Like the threat model in terms of security. Because it seems like if somebody were to write a legal value that was this random number, they could subvert the system. Is that correct?
If they know pi.
Yeah, that's correct. That's right.
Sure, but then they could just take a lock.
But it's different to take a lock and halt the system than to set
You don't
the
halt
value
this.
and
You don't
potentially-
halt the system. You make the garbage collection lock you. That's what will happen. You manage to write this, the garbage collection will lock, and you cannot proceed. Instead of this, you can just take a lock yourself.
I'm asking the other question, which is, can writing this specific value cause the system to have a semantic error, essentially, to break type
No,
safety?
no. So originally we thought, this is going to happen with such low probability. If it happens, we are willing to crash. But since we knew that people like you are going to ask questions, so when this happens, we'll just lock. This will solve the problem. So if you lock, you can move the object, without anybody creating any problem. You release the lock. Yeah.
You formulated it as if you choose a fixed prime, so fixed number.
Yeah.
Upfront. Can you change?
You can change it, but it doesn't matter theoretically. It's independent, so you can change this number all the time, or you can keep it the same as long as it's independent of your actions.
But it has a different threat model.
If someone is threatening to make you lock, and he's the program that is running, why you can take a lock, and that's it, right? It doesn't have to make you take a lock for him. It can just, crash itself, or yeah.
I guess I missed a step on the prior slide. So, what is it that causes the system to take a lock?
I didn't describe that. That happens with such low probability, and there are more interesting things to discuss. But it's once you see, so a write barrier. So the right, I don't know if we wrote the code. We wrote it, okay. We wrote and we debugged it with a 0, with pi equals 0. That happens. So.
You would get the question with high probability.
So the way you do it is you have a write barrier, and if ever anybody wants to write this pi, you block it. It doesn't go on
So you have
working.
comparison on every write.
A write barrier, yeah. A write barrier does a lot more than a comparison, so yeah.
How was this pi computed or determined in
How
any
was
given
this
system?
pi?
Yeah.
Yeah, you can say that the bits are not completely random on a real computer unless you get a piece of hardware to toss bits using physical devices. But you know, for our purposes, we believe it's good enough. Yeah, but you're right.
How is it chosen? How does in your system here? How is the value?
Yeah, I'll have to get back to the picture in the beginning to show you Philip. Philip basically implemented almost all. So basically, he implemented the Clover, and in this case, I really didn't worry about this. Maybe Bjarne has looked at the code, and you know how.
I've looked at the code, and the suggestion of thinking about Philip is a good one. The original code name for this thing was so the first like we called Cocoa for concurrent copying. He called this Clover Diet Cocoa. So
Okay.
the actual name he chose was a static name. A static number was D137C0C0.
Okay, he did Diet Cocoa. This was how it was chosen. Yeah. So as you see, it never happened. No, but he never implemented a better thing later. Okay, but it never happens. Okay, it just never happens. So you can. Okay, we've preached enough. I hope maybe we were convincing. The advantage is you don't have intermediate objects. You have quicker memory barriers, and the disadvantage is you may need to block really with very, very low probability. Never happens. Chicken, yeah.
What happens to bite-sized fields in the system?
You mean, this is a general question for all the collectors. I don't really care about fields. I care about words. So if you are accessing a double word, it's a problem for me. But if this thing is actually for integers, for the purpose of the logical access of the program, the collector doesn't really care about it. Okay, it treats it as a one word. It's a field for me.
You would fetch more data than
Yeah.
the program.
Yeah. Yeah.
So, I mean, it's good enough in practice. So where do you have the third solution?
Sure.
This writing this random pi seems like a good enough solution in practice.
Right. We'll have a better solution in practice. So, wait. Okay. So we are in chicken. Chicken is basically in practice. This may be the right thing to do. Is this videotaped? So I didn't say that. All of them are good and excellent. These are, yeah. Okay. So chicken. The idea is that the program is touching an object while the object is moved very scarcely. So this doesn't really happen a lot. And we can say, okay, let's optimistically try to move the object. And then if the program touches it in the middle, we just, give up on this object. We're not going to move it. So the collector, he copies the objects one by one in the background. And after copying an entire object, it checks if it was modified by the program. If not, then it puts a forwarding pointer said moved in an atomic operation, from null to a pointer to the next object. And objects are copied as a whole. The program, before it writes to a field, it takes this place that the forwarding pointer should be and atomically says, this is pinned. You cannot put a pointer in here. And then it goes and changes the object. So there is this, who touches first this forwarding pointer? The program that pins it or the collector that moves it and tells you that it has moved? Okay, and this is chicken. It's very, very simple. The advantage is you have no intermediate objects, no fallback to locking, quick memory barriers. The disadvantage is that you may fail to copy objects. So, sometimes an objects will not be copied. Okay, so let's compare them. So all of them are non-blocking, except for Clover that is also non-blocking, really. And then there is the time overhead, which gets better and better if you go down these collectors. and space overhead as well. Now, chicken may fail to copy, and actually stopless, because I didn't tell you the exact thing with the phases, there is a small phase where it doesn't copy as well, if you get there. So there is also a bit of failing to copy. Clover can be made to get rid of this problem. But if you have to choose a collector, and now I will say it off the record, so chicken seems very good for a choice if you're not really worried. So suppose you fail to copy 1,000 objects, and each of them sits on a separate page. Because, you know, there was this crazy thing that the program guessed which one you're going to move and just touch it as you were going to move it. Say 1,000 objects you didn't manage to copy. So you failed to, and say in worst case you failed to evict 1,000 pages, each of them of size 4K. So you have a 4 megabyte to pay for taking this thing, which is really fast. And 4 megabytes, you know, for the heap, people usually give a lot more space overhead for real-time collectors, and it's okay. It's not a big deal. So in worst case, this is really, you know, the program can make you fail to copy each and every object. But this, I don't have really a rigor distribution space when I say this, but this is really, doesn't sound very probable in practice. So you can fail a lot and still do very well in obtaining defragmentation. And so this one looks very good. If you want, so soon I'll give you some measurements. Yeah.
So in the chicken one, did you say that the program write barrier has an atomic hardware operation to set the forwarding pointer to the pin state?
Yeah.
Doesn't that impact its time overhead? When you're
Sure. There is an overhead.
in the comparison, I would have thought that the overall clover would have been much better since it didn't, you know, no atomic operations on the
In the write barrier? The write barrier, first you have to check that you're not writing a pi. I mean, we had some discussion like that about allocation, you know, pointer allocation. There's always, if you go to the code, eventually, there will be a lot of things you didn't think of it abstractly. And eventually you just look at the measures and they tell you which is better. But chicken is really, well, you can think of it as an atomic transaction, right? You try to copy the object and then someone touches it. If it doesn't touch it, there's not a lot of overhead. If it touches it, then you just give up. So there's not.
That's overhead the copying operation, but I'm talking about the program.
Yeah, so the program, what it has to do, it writes this thing in the write barrier. If you look at the generational garbage collection, right, it has a write barrier that will either put something in a buffer, right, or it will always write something somewhere, right? It can mark a mark bit table. This is the standard, and usually this will take like 2%. We'll be talking about 20% overhead. So, and much more for the other collectors, right? So it's hard to theoretically say what is exactly the overhead, but if we look at the code, it will be clear and the measurements will soon be shown. Yeah?
I just want to point out that Clover has to have an atomic operation in the write barrier too to make sure that you don't write high value. And if you do, then you have to take the lock.
Why is that?
I don't understand that at all.
Why does it have to be atomic?
Yeah, you know what value you want to write.
You have to, yeah, you're writing the 128 words and, so 128 bits, and you need to do that atomically.
Always.
Let's take this offline. I mean, if you look at the code, you will see that it's,
So if you had a non-atomic way to, and yeah, I mean, it's atomic, but it's not interlocked. It doesn't have to be interlocked.
you could make it faster if you didn't use a double word, but then the probability will be lower. You could, but these are technical details that we can discuss. So the overall picture, we've talked about real-time guarantees. The collection is completely concurrent, so there is no, it's not stopping the program. The program cooperates by these read and write barriers, which we've discussed a lot. there is a phase change operation that I will discuss in the next slide. And there is stack scanning that we've worked a lot on, and this is basically the bottleneck in the pauses. And so there is a separate project that I'm not discussing about that. We've done a lot of work there. And there is an assumption that the collector finishes on time, that this is what Ben was asking previously, and I talked about a bit. What is phases? So we want to avoid always using the heavy read and write barriers, and therefore we let the collector run in idle phases and then in copy phases. And the program is told which phase it runs in, and then it runs the appropriate read or write barriers. So in order to move from a phase to a phase, we could just block the program and then move to another phase. This is something that bothered someone here before. We don't do that. We use handshakes. This is a standard solution for concurrent collectors. So what happens is the collector says, now we're going to move to another phase. And the program threads once in a while check if the phase is changing, and they don't move all of them at the same time to the next phase. They do it with a handshake. Okay? And so it complicates things, because sometimes one of the program thread is already in a new phase and the other one is in a previous phase. This creates algorithmic complications. The gain is that you don't need to simultaneously block them, but the fuzzy move from phase to phase requires more work. This has been done before, so I'm not going to, well, I also don't have time, I'm not going to talk a lot about it. But this is a mechanism that lives there. Some results. This is the way RealTime community likes to check responsiveness. What you see here is a histogram, and so there is an event that's coming, and the question is how many times you made it to respond to it in 1 microsecond, in 2 microseconds, 3 microseconds, and so forth. So the non-copying collector sometimes does it in less than 1 microsecond, and most of the time does it in 1 microsecond, between 1 and 2. And let's look at stopless, which is the heaviest collector. What it does, if it's in the idle phase, it can respond pretty quickly, and then it will respond in 1 microsecond. But there is there is a bimodal behavior here. So you see that many times it takes him 4 microseconds to respond to the event, and that happens because it's in the copying phase, and it has all these barriers that are going on, right? But if you look now at Clover, Clover also has this this place where he's using the barriers and he's slower, but it's now in 3 microseconds instead of 4. If you look at Chicken, this is doing really great. So basically, this is here. Most of the times it responds within 1 microsecond. Very few times it responds in 2 microseconds, and you basically don't see it after that. And the event that we are looking at is a task of copying 64 pointers. Basically, we wanted to copy pointers because pointers have more barrier problems. So this is the heavier use of a copying. And copying is real-time tasks are many times to move, to copy stuff from some device to the memory, or this is the typical in audio, or you just move stuff in the memory. So we took this as a representing task for this check. So this is the response. Yeah.
Can one prove probabilistically that given a class of representative workloads and response time?
There is no real benchmarking system in the real-time community for high-level languages. It's the beginning of use of real-time in high-level languages, and we don't have many benchmarks. So we invented this, and you'll soon see that we check the overhead for standard benchmarks. There's not lots of projects in real-time high-level language. So this is difficult to compare and say, what's the general workload or what's the typical workload. It will be possible in the future, and then it will be easier to compare.
Do you have a model in mind of the class of realistic workloads?
No. No, so I mean, I could, even if I had a model in mind, I'm not very familiar with all the real-time applications to be an authority that could really, you know, I could really say this is a good model. I could work with someone who does real-time and then maybe produce such a model, but I don't have it, and others don't have it as well. Okay, the overhead. So we just took regular benchmarks, all our regular benchmarks, and checked the overhead with all these collectors, overall running time, with the moving done every 5 collections. This is the geometrical mean. You see that the overall for chicken, this on average is less than 20%. We did the same for JBB, which is a multi-threaded application. Yeah, so I was hoping to talk also about the compiler optimization, but the time is out. Yeah.
So I'm assuming that the memory model is shared memory model, right?
The memory model is?
It's shared memory model, right?
Yes,
So
shared
how
memory.
about if you have those local memory, you not know? So without the cloud-based overhead, have you
I cannot answer this online. I'll have to think about it. This is the architectures that we had to check it on, and we designed it for this. I don't know if the design would change if we had like a NUMA or something. Maybe it will, but I cannot answer immediately. Okay, how do I run over all this? Yeah. Okay, so we implemented this in Bartok. We have a few benchmarks. Okay, past specialization did a lot of... Actually, let's conclude. Okay, related work. There's a lot of related work. So, you know, part of it is mine, so I'm skipping. I'm hurting myself as well. I'm okay. So conclusion is we have a real-time garbage collector and a multiprocessor, which is lock-free, concurrent. It does compaction. It has high responsiveness. It has low overhead. And we have this new technology also with past specialization and incremental lock-free stack scanning. We've done some work in theory on formalizing what lock freedom is. This is basically what this project is about. And that's it. Thank you. And, yeah.
I guess one question I had was the degree to which you have to isolate sort of, so if you look at the real-time Java specification, there's this notion of sort of Java real-time threads, essentially, and they have a different memory model, a different memory allocator, et cetera. So with your system, do you see that as being necessary to have sort of separate threads that have the specific, you know, isolated memory space, or is it more the whole system, no matter what, is going to be real-time?
From the point of view of the collector, the whole system is going to be real-time. If you're really building an application, you can decide, you know, that some of your threads are going to use locks, are going to be, you know, interact slowly, do whatever they want, and some of the threads are going to respond to events. It's your ability when you're using such a system. No one is going to lock on your fast threads, and no one is going to connect threads that you do not connect because of memory issues. And that's guaranteed by this system. Now, you can design your program as in any way you like it, but we support you. Yeah.
So the IBM metronome work, the people involved with that have been pushing this distinction between time-based and work-based real-time GC.
Right.
And you guys seem to be completely rejecting all their arguments.
We don't really, no, not at all. We don't really need it. So if you think what is time-based versus work-based, you have a pause, right? And pauses in their collector, right? And you can think of pauses as coming because you do work or because the time has come, right? Now, if you don't have pauses, I don't care what triggers them because they don't come. Right? If I had to stop the program for something, I would have to decide if I stop it because the time has come or because it has done a lot of work allocating and I need to do something. But I don't stop the program. I just do it concurrently.
Let me rephrase what I think their position would be. That if you're going to have a real-time system, then you need to conservatively estimate the amount of garbage collection work per unit, mutator work you need to do.
Right.
And then you can schedule that garbage collector work as one of the real-time tasks in a real-time scheduling thing you have to do to have a hard real-time system anyway.
Right.
So that gives you larger than microscopic chunks of time to do things like copying. Therefore, you don't need to go through all the trouble you're going through. Do you find
right.
that
So
persuasive?
first, let me say that when they measure how much time they're giving the collector per minute, per second, they ignore the barriers. Okay. So if you're willing to ignore the barriers, I'm done. 0 all the time is devoted to application, and we're done with their kind of measurements. But to be fair, there is some work going on in the barriers, and you have to measure it. And since the rest of the world doesn't measure it, doesn't mean that you don't have to measure it. Okay, so we have some measurements for the worst phase where the barriers are the hardest, right? And then, so we've done some measurements about that, how much the time is, the execution time is deteriorating. And that can be used to schedule your work. There could be better scheduling things, like there are some works in the real-time community about scheduling, and they say, how much can I now schedule? If this program is going to run, how much of the CPU is it going to actually catch? And this depends on the phase in the program. And so you could have more sophisticated scheduling that know what's going to happen with the collector. There are some people who think about it, but we don't have anything like that in the literature. Okay. More questions? Yeah.
Could you use the same algorithms to do a generational garbage collector, to do a two-space or?
Sure. You just need. Yeah. So you have a mechanism for copying. So a generational collector doesn't have to do copying. You could do mark and sweep on the old generation, mark and sweep on the young generation, just collect more frequently on the young. And that is easy to do. I haven't thought if there is anything that requires a pause, but just on the top of my mind, I don't see anything that would create any problem with adding generations. Whether you want to do the young generation in a copying or in a mark sweep way. Okay?